This is the Solving Polynomials with Complex Zeros tutorial. Before we begin solving polynomials with complex zeros, let's discuss a little background information first. Remember the fundamental theorem of algebra. The fundamental theorem of algebra looks pretty complicated, but it's really a fairly simple concept. All it's saying is that any polynomial will have a number of roots equal to its highest exponent. So, for example, if we had this polynomial function would have 5 complex zeros. 5 complex zeros because the highest exponent is 5. Now, remember also that we say complex zeros, but complex zeros can be real numbers as well. It doesn't have to be something with an irrational number I. So 5 could be a complex zero. So just think of it really as it's going to have a number of zeros equal to its highest exponent. Now also when solving polynomials with complex zeros, you want to remember Descartes' rule of signs. Now let's walk through Descartes' rule of signs with this particular polynomial function. Remember that Descartes' rule of signs will help you solve for the number of positive and negative real roots, or real zeros, for a function. So to use Descartes' rule of signs, you want to take a look at the number of sign changes in your original function. So in this particular function, we have a positive 3x to the 5th plus 2x to the 4th plus 3x cubed plus 6x squared plus 5x minus 12. Now when you go from the first term to the second, there's no sign change. You're going from a positive 3x to the 5th to a positive 2x to the 4th. So we don't have a sign change there. Then when we go from the second term to the third term, it's positive to positive again, so there's no sign change. Then the third term to the fourth term, again, positive to positive, no sign change. Fourth term to the fifth term, positive to positive, no sign change. And now the fifth term to our last term, we go from positive to negative, so there's going to be one sign change. So according to Descartes' rule of signs, I'm going to have one positive real root, or real zero, if you want to call them zeros. You can also call them solutions. Roots, zeros, solutions, they all mean the same thing. Now the next step to Descartes' rule of signs is to solve for all the negative real zeros. So to do that, you want to plug a negative x into all of your x's. So it's going to look something like this. F of negative x is equal to 3 times negative x to the 5th plus 2 times negative x to the 4th plus 3 times a negative x to the 3rd plus 6 times a negative x squared plus 5 times a negative x minus 12. Now remember, when you're dealing with exponents to an odd degree, so in this case a 5, if the negative exponent was being raised to that odd degree, it's going to make it negative. Because a negative times any odd number of negatives is still a negative. And a negative raised to an even degree, like 4 or 2 here, is going to be positive because any negative times an even number of negatives is going to be positive. So for the case of f to the negative x, this negative x, because it's being raised to an odd number, is going to continue to be negative. So we're going to have negative 3x to the 5th. This negative x is being raised to an even exponent, so it's going to be positive. So plus 2x to the 4th. Then we've got another odd negative, so we're going to switch the sign. Because it was plus, I'm now going to make it minus. So minus 3x cubed. We've got another exponent to a even number of exponents, or another variable to an even exponent. So this is going to stay with whatever sign it currently has, and it currently has a positive, so it will keep that positive. So 6x squared minus 5x, because there's really an invisible 1 there, which is an odd exponent. So you're just going to leave that negative x as it is, minus 12. Now we want to use Descartes' rule of signs to count up the number of sign changes again. So we go from a negative to a positive, so there's one sign change. Then a positive to a negative, so there's another. a negative to a positive, that's another sign change, positive to a negative, that's one more, and lastly a negative to a negative, so there's no sign change there. So using Descartes' rule of signs, we know that there must be 4 negative real roots or some even number less than 4. And that's part of Descartes' rule of signs. You'll always have the number of real roots that you find, whether it's positive or negative, or possibly some even number less than the number that you began with. So because 1 has no even number less than it, you can only have one positive real root here, so you're guaranteed to have one. But you could also have 4 negative real roots, 2 negative real roots, or 0 negative real roots. You'll also notice that if you total up our roots, you're going to get 5 total roots, and that obeys the fundamental theorem of algebra. Because we're dealing with a polynomial to a 5th degree, we're going to have a total of 5 roots, 5 zeros, no matter what. Now there's one more thing I want to discuss with you before we start working on example problems. And that's the conjugate pairs theorem. The conjugate pairs theorem states that the complex zeros occur in pairs for any polynomial whose coefficients are real numbers. Any polynomial of an odd degree that has real coefficients will have 1 or more real zeros. So let me give you an example of that. A 4th degree polynomial whose coefficients are real numbers has 2 complex zeros. If one of those zeros is negative 3 plus 2i, what is the other? Now, to summarize the conjugate pairs theorem, you could basically say it as this. If you've got one complex zero that is negative 3 plus 2i, because that's what we were given here in the problem, then its conjugate pair for that complex zero is going to be negative 3 minus 2i. So you want to flip the sign in front of your irrational number. That's going to give you the conjugate pair of whatever zero or root or solution, whichever you prefer to call it, that you were given originally. So, armed with what you know from our review just now and what you know from algebra, let's do a couple practice problems. Determine the polynomial of the 4th degree that has real number coefficients and zeros of 2, 5, and negative 3 minus 2i. Well, if we're dealing with a polynomial to the 4th degree, it's going to look something like this. F of x is equal to ax to the 4th plus bx cubed plus cx squared plus dx plus e, and we know that the zeros that create that are 2, 5, and negative 3 minus 2i. Now because of the conjugate pairs theorem, you can look at that complex root and say that the other conjugate complex root that comes from that is going to be negative 3 plus 2i. So those are going to be the 4 zeros that make up this polynomial. And we want to determine what that polynomial is based on those zeros. So using the generic formula, x minus r, where r is one of your roots, we can determine what the actual roots are that are going to create this polynomial. You simply want to plug in these values that we've been given for that r in this generic equation. When you do that, it's going to look something like this. Our function that we're creating is going to be composed of these roots. X minus our first root, which is 2. X minus our second root, which is 5. X minus our third root, which is negative 3 minus 2i. And x minus our fourth root. And we're multiplying all 4 of these terms together to get our 4th degree polynomial. Let's begin by foiling these 2 terms together on the left. So we have f of x is equal to x squared minus 7x plus 10. And I got that answer by using our FOIL method, first, outside, inside, last. If you're having trouble with that, you want to review those tutorials that teach you how to do the foiling method. And I'm also going to factor this negative through. I'm going to distribute it through these parenthesis sets here and here. So when you distribute it through the parenthesis sets, we have x plus 3 plus 2y for our first parenthesis set, and x plus 3 minus 2i for our second parenthesis set. Now I'm going to come over here to the right and FOIL these two together. So we've got x plus 3 plus 2i times x plus 3 minus 2i. And I'm going to do my work here in red, and later we'll combine that work with the current function that we're building. So, in order to do this, I'm going to multiply our first term on the left parenthesis set through each term in the right parenthesis set. So x times x is x squared, x times 3 is positive 3x, and x times a negative 2y is a negative 2xi. Now I'll take my middle term and multiply it by each of those terms in the right parenthesis set. So 3 times x is positive 3x, 3 times 3 is 9, and 3 times a negative 2i is a negative 6i. Now our last term will multiply through each of these terms. So 2i times x is positive 2xi, 2i times 3 is positive 6i, and I'll go down below here. 2i times a negative 2i is a negative 4i squared. Now let's go ahead and combine our like terms to simplify this big statement. That's what we got by FOILing these two together. We've got 1x squared term, then we've got a 3x here and a 3x there, and that's all of our x terms, so those combine to make a positive 6x. Now I'm going to count up our xi terms. We've got a negative 2xi and a positive 2xi, so those will cancel. Now I'll take our irrational numbers. We've got a negative 6i and a positive 6i. Those are going to cancel each other out. One's negative and one's positive, and they're the same quantity. And then we've got this negative 4i squared. Now remember, I squared is equivalent to negative 1. So this is really like saying negative 4 times a negative 1, which is positive 4. And 4 plus 9 is 13. So everything in the red here FOILed down to x squared plus 6x plus 13. So we're going to take that and we're going to multiply it, since that was what this reduced down to, or FOILed down to. We're going to put this right back here so we can multiply it by that original two roots that we combined together. So now the function that we're building looks like this. F of x is equal to x squared minus 7x plus 10 times x squared plus 6x plus 13. And now you'll notice there's no more irrational numbers left in here. So we're building this fourth degree polynomial, and we've got one last step to do, and that's to combine these two terms together. So when we do that, we'll start again with the left and multiply that first term times all three terms in the right parenthesis set. X squared times x squared is x to the fourth. X squared times 6x is positive 6x cubed. X squared times 13 is a positive 13x squared. Now our second term, negative 7x, through all three terms. Negative 7x times x squared is a negative 7x cubed. Negative 7x times a positive 6x is a negative 42x squared. Negative 7x times a positive 13 is a negative 91x. And now our last term in the first parenthesis set, multiplied by all three terms here on the right. 10 times x squared is a positive 10x squared. 10 times positive 6x is a positive 60x. And 10 times a positive 13 is 130. So now we'll combine all our like terms because this is our fourth degree function. We've got f of x is equal to x to the fourth. Now we'll look at our x cubed terms. We've got a positive 6x cubed and a negative 7x cubed, which gives us a negative x cubed. And we'll get rid of those terms. Now we'll look at our squared terms. We've got a positive 13x squared, a negative 42x squared, and a positive 10x squared, which gives us a negative 19x squared. Now we'll combine our x terms. We've got a negative 91x and a positive 60x, which gives us a negative 31x. And that gets rid of all our x terms. And lastly, we've got positive 130 as our constant. And this is going to be the fourth degree polynomial that has the real number coefficients and zeros that were provided to us in this problem. Now let's take a look at one more example problem. Determine the complex zeros of the following polynomial function. So we've been given a fourth degree polynomial here, but we haven't been given any roots to help us get started. So to get started, I'm going to take all the factors of our constant term 9, and I'm going to put them over the factors of the coefficient before our highest variable, which in this case is going to be the invisible 1 here before x to the fourth. So our factors of 9 are positive and negative 1, and positive and negative 9, and positive and negative 3. And the factors of 1 are positive and negative 1, so I don't need to rewrite them. Now these are all the possible factors, and one of them may be a root here to this problem, or a complex zero. So we need to try them, and we're going to use synthetic division to try them out to see which one it is. So our first step, if you recall how to use synthetic division, we're just going to take the coefficients before each of our terms here. So before the x to the fourth, we've got 1. Before the x cubed, we've got 2. Before the x squared, we've got 10. Before the x, we've got 18. And then we've got a constant term of 9. And I'm going to try positive 1 as a factor. So we bring that first term down, 1, then we multiply it by the term out front, so 1 times 1 is 1. Then we add these two together and we get 3. Then we multiply 3 by what we've got out front, 3 times 1 is 3. We add these together and we get 13. 13 times 1 is 13. We add these together and we get 31. We multiply 31 by the front term there, 1, and we get 31. We add these two together and we get 40. Now if this had been a factor, or a root of our function, this would have totaled 0. So this positive 1 cannot be a root to this problem. Let's try it again. So we'll set it up, 1, 2, 10, 18, and 9. And let's see if negative 1 works. So I'll bring our 1 down. 1 times negative 1 is negative 1. 2 plus negative 1 is 1. 1 times negative 1 again is negative 1. 10 plus a negative 1 is 9. 9 times negative 1 is negative 9. 18 plus a negative 9 is positive 9. 9 times a negative 1 is negative 9. And 9 plus a negative 9 is 0. So that tells us that negative 1 is going to be one of the roots to this function. We can use that knowledge to help us find the rest of the zeros. So let's go to step 2. Step 2 is to take that root in the form of x minus r, and since our root is negative 1, x minus a negative 1 is x plus 1, and we're going to use polynomial long division here. Underneath the division sign, we're going to put our function. Alright, so what do we have to multiply x by to get x to the fourth? Well, we'd have to multiply it by an x cubed. So we take that x cubed and we multiply it by the x first, and we get x to the fourth. And then x cubed times 1 is a positive 1x cubed. Now we want to subtract these terms. X to the fourth minus x to the fourth is 0x to the fourth. And 2x cubed minus x cubed is x cubed. So now we ask, what do we multiply x by to get x cubed? Well, we'd have to multiply it by a positive x squared. And I'm also going to bring down these terms that were still remaining. So we've got positive 10x squared, positive 18x, and positive 9. So we know that we're multiplying x squared by x to get x cubed, and then x squared by positive 1 to get positive x squared. We're going to subtract these two terms. X cubed minus x cubed is 0. 10x squared minus x squared is 9x squared. We'll bring down our positive 18x. and we'll bring down our positive 9. So now what do we want to multiply x by to get 9x squared? Well, we want to multiply it by a positive 9x. 9x times x is 9x squared, and then 9x times that 1 right here is positive 9x. Again, we'll subtract. So 9x squared minus 9x squared is 0. 18x minus 9x is 9x, and then we'll bring down our 9. So now we have 9x plus 9. We want to ask, what do we multiply x by to get a 9x? Well, we multiply it by a positive 9. So 9 times x gives us 9x, and then 9 times this 1 gives us 9. We want to subtract. 9x minus 9x is 0, and 9 minus 9 is 0. So we do know that x plus 1 was a factor. And when you factor x plus 1 through this polynomial equation that we've been given, you get this polynomial equation up top. So we can now take that polynomial equation from up top, and in step 3, we're going to go ahead and use synthetic division to solve for its possible roots. So we've got x cubed plus x squared plus 9x plus 9. And again, we want to check for the possible roots of this expression. To do that, we take the factors of our constant term 9 and the factors of the coefficient before our highest variable, which in this case was 1. And those factors are just like we had before, positive and negative 1 and positive and negative 9, and positive and negative 3. So we want to run those through to find another real root. So I'll start with negative 1. We'll create that same box where we use the coefficients from our polynomial. So we've got a 1 in front of the x cubed, a 1 in front of the x squared, a 9 in front of the x, and our constant is 9. And we're going to be checking to see if negative 1 is a factor. So we'll bring that first term down, 1. 1 times negative 1 is negative 1. We'll add these two. 1 plus a negative 1 is 0. 0 times negative 1 is 0. We'll add the 9 and the 0 to get 9. 9 times the negative 1 out front is negative 9. And 9 plus negative 9 is 0. So it turns out that negative 1 is a factor of this expression now too. So now we know that negative 1 occurs twice as two roots for our original polynomial function. And knowing that negative 1 is a factor of this function, we can go ahead and use polynomial long division again to reduce that function. So in step 4 here, and I'll make some room by getting rid of this synthetic division that didn't work out for us. So we know that negative 1 is a factor, so we're going to take x minus our root, which is negative 1, so x minus negative 1 is x plus 1. And we're going to be dividing this expression by that x plus 1. So I'll put that under our division here, x cubed plus x squared plus 9x plus 9. Now what do we multiply x by to get x cubed? Well, we multiply it by an x squared. We take that x squared and we multiply by x to get our x cubed, and then x squared times 1 to get positive x squared. We subtract these again. X cubed minus x cubed is 0. X squared minus x squared is 0. We'll bring down these terms, 9x plus 9. And we want to know, what do we multiply x by now to get 9x? Well, we multiply that by 9. 9 times x is 9x, and 9 times positive 1 is positive 9. We'll subtract these again. 9x minus 9x is 0, and 9 minus 9 is 0. So we do know that that negative 1 was one of our roots. And it leaves us with this expression here, x squared plus 9. Now when you're solving for roots, that's solving basically for a value of 0 here. You're setting your entire polynomial expression equal to 0. So we're going to take this now and set it equal to 0. That'll help us find our last two roots, which are going to be complex. I'll go ahead and do step 5 in a separate color so that our work doesn't merge. So we're going to set that expression x squared plus 9 equal to 0 and solve for the value of x. First thing we want to do is subtract 9 from both sides of the equation, and we get x squared is equal to negative 9. Now we want to solve for x, so to get rid of that x squared, or that squared term, I'm going to take the square root. The square root will cancel the square, and we have x on the left. On the right, we're going to have a positive or negative. The square root of 9 is 3, and we'd be left with a negative 1 under the radical, and you know that I is equivalent to negative 1. So x is equal to positive or negative 3i. Those are going to be the two complex zeros for this problem. And that's what they were asking us to find, was the complex zeros. But just for your information, let's take a look at all the zeros that we found. If we took our expression, f of x, and made it just the roots, we'd have x plus 1, and that was the first root that we found using synthetic division, and then x plus 1, because that was the second root that we found using synthetic division, times x plus 3i times x minus 3i. And those were from the last two roots that we found, which were the complex roots. Now if you were to multiply all four of these roots together, you'd get our original polynomial expression. So that's how you could take a polynomial expression that you've been given without any zeros and find all the zeros for that expression. It just takes a little bit of time.